All right, so yesterday we talked a little bit about the Z2 cross Z2 SPT as a preparation for the non-invertible SPT. So I want to set up the convention and the framework for ordinary SPT, and then it should be clear how to generalize it to non-invertible SPT. So last time we talked about two very trivial Hamiltonians. And both of them are trivially gapped with a unique ground state. For this product Hamiltonian, the ground state is a product state. Whereas for this slightly more non-trivial Hamiltonian, the cluster Hamiltonian, the ground state is, well, let me call it the cluster state. And it's simply related to the product state by unitary transformation, where CZ is the control Z gate. Now, without imposing the symmetry, the two Hamiltonians are completely equivalent. Both of them describe a trivially gapped phase. But the claim is that the moment you impose this Z2 cross Z2 symmetry generated by eta even, which consists of the product of xj over all the even side, eta odd, consists of product of xj over all the odd side, then they become distinct Z2 cross Z2 SPTs. So let me briefly describe three ways to distinguish these two phases the moment you impose the symmetry. I'm not saying that these are the only three ways, but these are three ways that can be directly generalized when we talk about non-invertible SPT. And my presentation will be slightly different from the conventional one you can find in textbooks, but this is for preparation so that to generalize to the non-invertible one. Okay, so the first way of detecting the difference between the two is via the edge mode. So far it sounds like the standard story, but there's a slight difference in the presentation. Okay, so generally, how do you compare two different objects? Well, the best way to compare them is to put them side by side, and that's what we are going to do. So our space is still a closed periodic chain. So this part is a little bit different from the way people usually detect the difference between SPTs, where they put this SPT on an open chain. But I want to put both of them on a closed periodic chain. But for half of the chain, let me look at my convention, I will use the cluster Hamiltonian. But for the other half, I will use the product Hamiltonian. So in total, my chain has L site. But I'm choosing some intermediate site, L prime, to split the closed chain into two halves. And in this half, I'm going to put the cluster Hamiltonian. In this half, I'm going to put the product Hamiltonian. And you can, the interface is that here and there. And the claim is that you are going to see non-trivial edge mode at the two interfaces. And as throughout, I'm going to assume L to be even. Later, I'm going to assume L to be a multiple of 4 for simplicity. Okay, so this is just a cartoon. What's the actual Hamiltonian I'm going to work with? The actual Hamiltonian I'm going to work with, I will call it H interface. Minus Z1, X2, Z3, minus Z2, X3, Z4, and minus dot 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 all the way to minus Z L prime minus 2, X L prime minus 1, Z L prime. So this part is the Hamiltonian here, where I just put down the ordinary cluster Hamiltonian. Starting from here, I'm going to put the product state Hamiltonian. Okay, so that's it. All right, so I at the interface, deep in the a region here or here, there's no ambiguity. You just use the cluster Hamiltonian or the product Hamiltonian. At the interface, you do have some freedom. Here I have made a choice for that freedom. And I made a simple choice such that all the terms in the Hamiltonian, in this interface Hamiltonian, still commute with each other. This will make my life much easier. But the claim is that whatever I'm going to say in the following will not depend on this choice, as long as I preserve the symmetry.
So you also require to preserve the symmetry?
Yes, I'm getting, yes, definitely. So let's see. This Hamiltonian, this interface Hamiltonian, preserves the symmetry eta even and eta odd, as we can easily verify. One advantage of insist on working on a closed periodic chain is that I never have to break the symmetry operators. I always have this product of X on a closed periodic chain. In the more conventional presentation, people usually break the symmetry operators, and there's no problem with that if you work with the on-site symmetries. But I chose this presentation just because for the later non-invertible symmetry, it's a little bit more subtle on how to break it. So that's the reason for this presentation.
May I ask a question?
Yeah.
So if you do not impose symmetry, is there an easy way to see that the two phases are the same? Is there a path where you can show that it's always gapped?
Yes, and one way to say that is that you can just impose you can just do the unitary transformation, and that unitary transformation, where did I write it? The one over there, the product of CZ, is a finite depth local unitary. You can split the product over J into even J and odd J, so it's steps 2. In each step, there's no overlap between the local operator. And from a finite depth local unitary, you can turn it into a continuous deformation between the two Hamiltonians.
I'm a little worried that these two ground states, they are orthogonal in the thermodynamic limit. That doesn't matter?
I think the statement is that you still have a continuous deformation connecting the two. They don't coexist at the same time. Okay. But the moment you impose the Z2 cross Z2 symmetry, you see that each individual CZ gate is no longer Z2 cross Z2 symmetric. Okay. So far it's just a very innocent modification of what we usually do by putting the system on an open chain. The connection is that you just put the coefficients here to be infinite so that you pin down all the qubits on this half. And then the system is effectively on an open chain. Okay, so let's study this Hamiltonian. So first, it's easy to see that every terms commute with each other. I didn't put XL prime because that would not have commuted with this guy, even though it preserved the symmetry. So I chose this interface Hamiltonian just for simplicity. So I have how many terms over here? So it's going from 2 to L prime minus 1. So I have L prime minus 2 terms. Here I have L minus L prime terms. So in total, I have L minus 2 commuting Pauli projectors. This is 2 less than the system up there. So I have L qubit, but only L minus 2 constraint. And that leads to 4 ground states. So the interface system has 4 degenerate ground states. You can think about 2 of them localized here, 2 of them localized there, as we will see more explicitly later on. Okay. So it's a very simple system to solve. Now let's try to understand the 4 ground states in more details. So let psi be any state in the ground space. So we have a 4-dimensional ground space, and psi can be any vector there. Now, what do psi satisfy? Psi, by definition, satisfy, because it's a commuting Pauli Hamiltonian, I'm able to diagonalize every term at the same time. So I have the zxz equals 1 for j equals to 2, 3, all the way to L prime minus 1, and xj equals to 1 for j equals to L prime plus 1, all the way to L. This is the eigenvalue of the state under these operators. Now, using these constraints, let's see what happens to the symmetry operator. Let's start with eta even. So eta even, when you act on this ground state, so eta even is x2, x4, x6, all the way to xl prime minus 2, xl prime plus 2 to xl. Okay, all the even guys. Oh, I'm only also assuming L prime to be even for simplicity. Okay. And now we can use all these constraints to simplify this. So at x2, so here j can be 2, is z1, z3. x4 is z3, z5, and so on. And when we get to this point, I think I still have zl prime minus 3, zl prime minus 1. But for this guy, I cannot do anything because it doesn't belong to any of the lists here. But then for this guy, I'm just going to set it to be 1. Okay? Good. So the z's, the intermediate z's all cancel. Let me just make sure I'm doing this right. Yes. And I'm left with what am I left with? Eta even. I'm left with z1, zl prime minus 1, xl prime, acting on psi. Okay, good. So we see something interesting here. Eta even originally is an operator that involved the product of all the x, all the even x on the entire chain. But if you act on any state in the ground space, when you restrict to the ground space, it factorizes into a local factor on the left and a local factor on the right. Remember, the 1 region is here, the L prime region is over there. So let's give them some names. This factor, I'm going to call them eta left even. So this stands for left, whereas this stands for the number of sides. It's a little bit confusing. Apologize for that. It actually makes sense because the left region is close to the L side. And let's call this factor eta right even. Okay. All right. Similarly, if you compute eta odd acting on psi, you can, by the same trick, show that it factorizes into x1, z2, zl prime psi. And I can call this factor eta left odd, this factor eta right odd. All right. The global eta even and eta odd, they commute with each other. They realize the z2 cross z2 linearly. There's no projectivity whatsoever. But if you look at the local factors, you see something interesting. In particular, eta left even and eta left odd anti-commute. This is x1, z2. There's a z1, so they anti-commute. Similarly, x r even and x r odd anti-commute. So it means that you have some local projective algebra on the left interface and on the right interface. Such a projective algebra does not admit a one-dimensional representation. The minimal representation is two-dimensional representation. So you get a twofold degeneracy on the left interface and on the right interface. In total, that gives you a four-fold degeneracy. Okay. All right, so that's for the standard Z2 cross Z2, and the fact that you have this edge mode implies that these are two distinct SPTs. You can further add deformation to the interface Hamiltonian while preserving the Z2 cross Z2 symmetry. The argument is that the edge modes remain robust. The reason is because as long as your deformation is local and preserve the Z2 cross Z2, the eta even and eta odd, they still act within the ground space, because you preserve the symmetry. And because the deformation is local, the operator will still factorize into a local factor on the left and a local factor on the right. And there's no way you can change the minus sign continuously. So the projective algebra will still be there. Okay, any question for this review? All right.
So if you have the formation of the Hamiltonian, how do you construct this eta left, eta right? Here
That's right, yeah.
multiply.
Yeah, if you add a general deformation, it's hard to write down the eta left and the eta right.
But we claim that they still exist.
Yeah, the argument is by locality, right? Because if factorizing to two local factors, if you turn on some small deformation, as long as the deformation is symmetric and local, it's not going to correlate the two. So that's the reason why picking this particularly simple interface Hamiltonian helps, because in this system we can write down eta left and eta right explicitly. Okay. Good. Another way to say that the two faces are different, or is via the finite depth local unitary circuit. But I'm not going to say too much about it. So without imposing the symmetry, the cluster and the product state, they are related by this CZ, product of CZ. And you can split the product into even and odd, and then it's a depth 2 circuit. And one can define the phases of matters between the state to be such that two states are in the same phase if they are related by a finite depth local unitary. But the moment you impose the Z2 cross Z2 symmetries, you see that the local factor, namely the CZ, they are not Z2 cross Z2 symmetric. And I think it's a more non-trivial statement to show that there does not exist a finite depth local unitary that is locally Z2 cross Z2 symmetric to connect the cluster with the product state. Okay, so let me just, so I'm going to be very brief about this. Yes.
Yes, here. May I make sure the first part of H-cone, did you try to construct the four distinct states, ground states, out of this?
This gives a characterization of the four degenerate ground states for the interface system.
And you can write down, maybe you already write down, but you are able to write down four distinct ground states.
Yeah, well, I didn't write it down, but I give a more invariant characterization, which is that they are the minimal two-dimensional representation of these four operators. But it's an exactly solvable Hamiltonian, so you can also write it down.
But maybe you can describe that well. Suppose there's one ground state you know, or how do you switch between different ground states? Maybe some operators.
Yeah, definitely. So if you start with one ground state, right, so you can act with one of the etas, that will take you to a different one. Right, let's just focus on one projective algebra. This algebra has a two-dimensional representation, and the way it acts is that let's call them A and B. Right, the A will take one state to the other, and B will take the other state back. It's a standard two-dimensional representation for this AB equals minus BA algebra.
How will you argue that at one endpoint of the symmetry operator acts in the space?
Sorry, say again?
How would you argue that? So you're kind of assuming that one endpoint of the symmetry operator acts within the ground space.
Oh, you can also check in this model. Let's see, this guy commutes with the entire interface.
So is that something general? Yeah, I can check.
Right. So indeed, in this simple model, this is obvious. And then as you add deformation, let's do it in steps. First, assume the deformation is symmetric. So that means eta even and eta odd globally still act within the ground space. Okay, I'm not yet factorizing them. At this point, let's forget about the Hamiltonian. You have a ground space, eta even and eta odd act within that four-dimensional ground space, that ground space. Now, second, the deformation is local. And therefore, eta even and eta odd should still factorize into two separate local factors. By locality, these two factors will commute with each other, and therefore they have to be separately act within the ground space. Yeah. Okay. Now let me get to the third description, which will also be important when we try to construct the non-invertible SPTs. This is known as the Kennedy Tasaki transformation. All right. So the idea is that it's very subtle to distinguish these two Hamiltonian. But what Kennedy and Tasaki realized is that instead of directly working with these two Hamiltonians which have the same spectrum, why don't we just do some manipulation, some transformation to map them to two other Hamiltonians that look more distinct? The way they phrase it is that they perform a non-local transformation known as the Kennedy-Tasaki transformation. But from in the thing of this school, you can interpret the Kennedy-Tasaki transformation as gauging the Z2 cross Z2 symmetry. To be more precise, this is a twisted gauging. And in the high energy literature, this gauging is usually denoted as TST. So S stands for the modular S transformation, where T stands for the modular T transformation, related to what Ifan talked about in his lectures. But we don't have to use this terminology here. Let me just spell out what this transformation does. So it maps Xj. I feel like I should use a new blackboard. Maps Xj to X hat j, and it maps Zj minus 1, Zj plus 1 to Z hat j minus 1, Xj hat, Z hat j plus 1.
You use arrows again.
Yes, purposely, because it's the same kind of arrow that we had in the first lecture. So let me put it in quotation mark, and the next thing is that we should make it precise. That's an excellent point. So indeed, you see, this is exactly the same kind of arrow, because if you take the product of z's on the entire chain, on the left-hand side, it becomes 1. But on the right-hand side, you get something non-trivial, the product of x hat. It's not a coincidence, because as we discussed in the first two lectures, the arrows there stands for a transformation implemented by a non-invertible operator. And that's related to gauging. And this one is also related to gauging. So later on, I'm going to write down the operator that implements this arrow explicitly. But for now, let's just take it as a transformation. And when we get to the non-invertible part, we'll write down the operator. So after this transformation, you'll find that the new Hamiltonian here is this, whereas this one goes to okay. So that you can easily check. But now on the right-hand side, there's an invariant ways to distinguish these two headed Hamiltonians. This Hamiltonian is a trivially gap phase, just like the one we started with. This one, on the other hand, represents a Z2 cross Z2 spontaneously broken phase. So this Hamiltonian has one ground state, among other things. This Hamiltonian will have 4 ground states. Note that this is J minus 1 versus J plus 1. So you only have to correlate the spin on the even side and correlate the spins on the odd side independently. So that leads to 4 state. So this is a Z2 cross Z2 unbroken phase. This is a Z2 cross Z2 broken phase. So the upshot is that instead of distinguishing the two SPTs directly on the left-hand side, after you do the gauging, or equivalently doing the Kennedy-Tasaki transformation, you map the two SPTs into 2 different symmetry breaking Hamiltonians in the usual sense with respect to Z2 cross Z2. And we know how to distinguish Hamiltonians that represents different global symmetry breaking pattern, and thereby that gives you another way to distinguish the two SPTs.
So these transformations do not involve in translation, right? Just totally internal.
That's right. That's right. And that's my next slide. Yes. Okay. So these are 3 ways to distinguish the SPTs. And as was already anticipated by the questions, we should try to make this arrow more precise. And related to that, there's going to be a new symmetry of the cluster model. Yes.
So is the statement here that different sort of global variants of a theory, if different global variants of a theory are in different phases, then all then the ones that are ungauged also have to be in different phases?
So let me phrase it in the continuum way, in the spirit of Mac's lecture. These 2 SPTs represent 2 different invertible field theories. Both of them are invertible. So if you quantize it on any manifold, well, we're in 1 plus 1D, so pretty much the circle is the only option. If you put both of them on a circle, you get 1 state. And if you don't impose any symmetry, you don't see the difference. The statement is that starting from this 2 invertible field theory, you gauge the Z2 cross Z2 symmetry in some manner. And then you land on an invertible field theory in this case, and a non-invertible field theory with 4 states on the right-hand side. This is not in tension with the fact that if you forget about the symmetry, these 2 phases are the same. Because when you perform the KT transformation, or equivalently when you do the gauging, you have committed to a particular global symmetry. So, so the choice of the symmetry happens here, and therefore resulting in 2 different symmetry breaking patterns. And the key word in this context is that there's no order parameter to distinguish these 2 phases because they really look the same. But there's no local order parameter. But if you go to here, there's a local order parameter distinguish the 2 symmetry breaking patterns. And those local order parameter over here becomes a non-local string-like order parameter here. So the key word in this discussion is the string order parameter. But I'm not going to write on the, I'm not going to say too much about the string order parameter. Okay, so those are the reviews. And now I think with this warm up, we can march into the non-invertible world. Any other questions before we proceed?
Yeah, sure. So the Z2, after you do the Nagitasaki, that's not the same Z2 over here, right? It's a different.
Oh, very good question. You see, in the paper, we add sufficiently many hats and superscripts to distinguish them. But when I roll over there, I ran out of space, so I was being sloppy. But since you ask, I should come back. Here, I just say it's a symmetry preserving phase of some Z2 cross Z2. But which Z2 cross Z2? I should be precise about that, and thank you for the question. There's a hat here. There's a hat here. So strictly speaking, I should put hat there. And indeed, it's a very good question because here we have a Z2 cross Z2 global symmetry without a hat. In going from the left to the right, I repeatedly emphasize we gauge the symmetry. If a global symmetry has been gauged, you can no longer talk about its symmetry breaking patterns. So here, the symmetry breaking is with respect to a different Z2 cross Z2 symmetry. So the idea is that if you start with a system with a Z2 cross Z2 global symmetry and you gauge that global symmetry, there's going to be a dual global symmetry. And in this case, it's generated by the product of x hat j over the even side and x hat j over the odd side. If you drop the hat, it's tempting to identify the 2. But it's really important to distinguish them. Yeah. One of them is dual to the other. Yeah, very good question. Thank you. And that will become even more important when we get to the non-invertible case. Here is you might easily confuse the 2 Z2 cross Z2 because they take the same expression. They are just product of xj or x hat j. But later on, we will see that even the symmetry group or fusion rule will be different. Yes.
And is this one specific example where we know such a transformation and then have an order parameter to differentiate between the 2 Hamiltonians, or are many examples like this? No?
Okay, so again, I always don't want to answer something too general. Yeah. So let's. I think many people ask me that. I'm not sure. Probably there are some cases you cannot distinguish. let me not commit to that. I don't want to make a comment about it. Yeah, I like to work with simplest example. Any other question? It's a good question. It's just I don't have the answer on top of my head. All right, good. So what we just concluded is that the product state and the cluster state, there are distinct Z2 cross Z2 SPTs. And yes.
What seems like the KT transmission is just like at least for the first one, for the XJ just seems like a change of variables, like you're just adding a hat.
That's right. But the non-trivial thing happens on the second line. Right. So I didn't explain that. Because I didn't even define what gauging means on the lattice. Yeah. That will probably take me 20 to 30 minutes, so I didn't do it. Later I'm going to write down an operator that implements this transformation exactly in the same sense as we discussed in the first lecture. Regarding why this is gauging, I didn't explain in the lecture. And I probably won't have time to do it. But let me say it in words. So you have this Z2 cross Z2 symmetry. They are on-site symmetries, so you can attempt to gauge them. And when you gauge them, you literally just introduce gauge fields on the links. Well, in this case, they will be on the site. And you impose the Gauss law and couple the Hamiltonians to the gauge fields minimally. And after some manipulation, you will arrive at a new Hamiltonian. And the claim is that the new Hamiltonian, namely the gauge Hamiltonian, is related to the old Hamiltonian, the ungauged one, by that transformation. Yeah. But I didn't derive that. So we did that in the paper, though. Okay, good. Okay, so we just explained why the cluster and the product states are two distinct Z2 cross Z2 SPTs. And notice that in the presentation, I didn't say which one is the trivial SPT and which one is the non-trivial SPT. I would say on general grounds, without specifying a Hilbert space or without specifying the symmetry operator, the expression for the symmetry operator, the notion of SPT is always relative. So the most invariant thing you can talk about is the difference between two SPTs. Once you have made some choices, you can say which SPT is more trivial than the other. But I'll try not to commit to such a notion of a trivial SPT because it definitely won't apply when we go to the non-invertible SPTs. And that's why I prefer this presentation where we detect the relative difference between the two SPTs. Okay. So the next thing I'm going to talk about is we're going to look at the cluster Hamiltonian. We see that it has the Z2 cross Z2 symmetry, but it also has a non-invertible symmetry. And let me just write it down. It has many more symmetries, but I'm going to focus on the non-invertible one and argue that the cluster state can be viewed as a non-invertible SPT. Okay. So the non-invertible symmetry will be denoted by D, but I have to say that this D will be different from the D in the Ising model. But it's a new day and it's a separate lecture, so I hope that is fine. And the way this D acts, and by acts I mean the following, dxj equals, sorry, I have to find a typo in my note, is zj minus 1, zj plus 1, d. Zj minus 1, zj plus 1, xj. Okay. So let's first check the cluster Hamiltonian will commute with this operator d, right? Because you just swap xj with the neighboring zz and vice versa. This is different from the Kennedy-Tasaki transformation, and we'll get back to that in just a second. Now the question is there such an operator that implements this transformation? Again, this transformation cannot be unitary, because as you take the product of the z's on the right-hand side, you get 1. But on the left-hand side, you get the product of x, which is non-trivial. So that's the same kind of argument. In fact, this D can be written in terms of the Kramers-Wannier operator we talked about in the first 2 lectures. All right, so what are D even and D odd? D even is the Kramers-Wannier transform operator we discussed early on the even side. And this is the Kramers-Wannier transformation on the odd side. And and T is the lattice translation by one side. Okay. So from this expression, it should be clear why D implements this transformation. Because let's say J is even, so D odd doesn't talk to X even. D even will map Xj to Zj, Zj plus 2. But then you do a lattice translation to bring it one step back. Okay? Any question at this point? Okay, at this point you could have asked, why bother with the lattice translation here, right? Even without the lattice translation here, this product of D even and D odd leaves the cluster Hamiltonian invariant. So that's also a good symmetry. That is true, and we can also discuss that one. But this one is, in a sense, simpler than the Kramers-Wannier one, and also simpler than the product of 2 Kramers-Wannier. And let's see why. So first of all, D times eta even equals eta even times D equals eta odd times D equals D times eta odd equals D. This is easy to see because each factor, D even contains a projection of eta even, D odd contains a projection of eta odd, so they will absorb both eta even and eta odd. The interesting one is D square. D square turns out to be 1 plus eta even, 1 plus eta odd, and that's it. There's no mixing with the lattice translation. And intuitively, that's clear. When you do D even, you do a half lattice translation on the even side. Well, actually, it's one lattice translation on the even on this chain. And on the odd, you do the lattice translation on the odd side. And then they are canceled by this translation. So in total, D doesn't implement a lattice translation. It's also clear from this expression. Xj is on the J side. After you do the transformation, you get Zj minus 1, Zj plus 1, which you can think of it as center on the J side. So this operator doesn't move the local operator. That's why when you square it, you don't get any factor on the right-hand side. This is to be contrasted with the Kramers-Wannier symmetry we talk about in the Ising model, where when you square it, you get 1 plus eta times the lattice translation. And we argue that in the Kramers-Wannier case, if you want the operator to act locally, in some sense, there's no way you can get rid of the mixing with the lattice translation. But the moment you have Kramers-Wannier on the even side and on the odd side, you can undo that lattice translation, and thereby getting something more internal. So it's a very simple exercise to verify this transformation, and I wrote it in the exercise. And for this D, D also equals D dagger, as you can check. Okay, so this non-invertible symmetry of the cluster model is really as close to the continuum fusion category as possible, unlike the Kramers-Wannier case, where it involves a lattice translation. So which fusion category is this one? Well, from the data I just gave you, it's actually hard to determine the fusion category. The reason is because the fusion rule between this operator does not uniquely determine the underlying category. In fact, I didn't even say anything about category in my lectures, so I will not use that language extensively, but let me just say the answer in case some of you are interested. The fusion category, as it turns out, is the representation of the dihedral group of order 8.
Don't be alarmed by this. This is just a test.
It's not a statement about my lecture.
On every first Wednesday of every month at 11:45.
Okay. So you can, one thing you can easily verify is that you can you can go to the Wikipedia page to look up for the irreducible representation of the dihedral group of order 8, and this is precisely the tensor product of the E-reps for D8. And D stands for the two-dimensional representation of D8. The various etas stands for the one-dimensional representation of D8. And this is the product, the tensor product between them.
So Shu-Heng,
Yes.
for Kramers-Wannier, we need the Hamiltonian to be translation invariant. But here, in order to have this symmetry, we don't.
You don't have to. Yeah. So in fact, you can put different coefficients in front of the ZXZ, but you still have this symmetry. That's right.
Yeah. So how D is normalized? You normalize D by when D arctan the vacuum is became identity.
Right.
Or whether, but this if you do that,
It's not the identity. There's a two. There's a two.
I think for the even talk, there's normalization of D. You can shrink. Let me see.
Yep.
So there is a D. Let's say.
Yeah. The way I normalize D is such that if you act, actually, I think that's one of the homework problems. Yes. So you can show that D acting on the cluster state is 2 times cluster.
Yeah. So why you put the 2 there?
Right. So it's the same question. You ask for the Kramers-Wannier. And at that time, I didn't give you a satisfactory answer on the lattice. And today, I still cannot give you a satisfactory answer. So in the continuum, there's a very natural way to determine the normalization. On the lattice, I don't have a completely well-defined way to determine it. All I can say is that I choose the normalization such that it matches with the continuum. The best explanation I can give on the lattice is via the MPO. So yesterday, as we saw in the MPO presentation for the Kramers-Wannier operator, somehow that picks up the root 2 for you. Okay. Yeah. But it's a very interesting question because as Yifan will explain in his lectures, the way he will fix the normalization of the various topological defect line is to use modular covariance. But it's not clear what that means on a Hamiltonian lattice model.
How do you know it's D8 and not Q8?
Good. So yeah, so that's exactly the caveat I was saying. So from the presentation I gave, you could not. The way we determine it is that we start with the cluster Hamiltonian, and you can do some gauging, and you will find the D8 symmetry in the gauge model. That implies the symmetry has to be D8 because that would be the quantum symmetry. That's right. More alternatively, you can just directly compute the F symbols on the lattice.
So there is no mix with the translation, so it is possible to determine all the F symbols.
That's right. That's right. That's right. That's right. So all these F symbols are well defined. Yeah, exactly.
Just to be sure, so the other version of capital T without the T inverse, that will, in the continuum, that becomes the rest HA generator, right?
So that's a good question. It depends on the Hamiltonian.
For this Hamiltonian, with translation.
For this Hamiltonian, it's hard to say because the low energy theory is an invertible field theory. So the better example would be you can take 2 Ising models, one on the even side, one on the odd side. That model will have the same set of symmetries. In that case, the one without the T inverse becomes the rep H8. Yes.
But D square will have the translation.
Yes.
So in the rep D8, whether this D eta E eta O will be the object, a simple object in the rep D8.
So D times eta even?
No, just D and eta E and eta O. Whether these 3 can be viewed as simple object in rep D8.
Right. So the simple objects are 1, eta even, eta odd, eta even times eta odd, and D.
I see. And the fusion rule is basically what you write down there. That's sum. Operator sum became
And you can see, you can check that, there are 5 simple objects here, and that corresponds to the 5 irreducible representation of D8. Yeah, 4 of them are one-dimensional, and there's a non-abelian 2-dimensional representation.
Yes. Does there exist still a Majorana-Fermian model where this D becomes invertible, just like in
I think so. That's a good question. I didn't work it out. I think so. I didn't work it out. Okay.
So for the normalization, could you just argue that if you multiply D by 2, then it wouldn't be a simple object anymore?
Well, but it depends on what we mean by a simple object on the lattice.
Okay,
right?
but sorry, when you squared it, right, you then get like 4 plus something.
Yes.
Right.
So what was wrong with that as an operator in a lattice model? The notion of simpleness is very special.
Yeah.
It's something that you can unambiguously define in continuum field theory. You can unambiguously define in fusion category. Yeah. You can also define it for defects, namely twisted boundary condition in a Hamiltonian lattice model. But if you just talk about operators, I don't know how to define it. How would you define it?
Okay, yeah, so, but you don't want to just like appeal to the fusion category, or?
Well, that's basically the answer I provided. So I normalize the operator such that it matches with the continuum. But I don't have an intrinsic definition of simpleness, just with respect to the lattice operators.
Okay.
Yeah.
So usually in physics, everything that is allowed happens. Shouldn't we be very surprised that here you only get integers in the fusion rule in the lattice model? Because you say the only way to get integers is because there's maybe a continuum limit or a fusion category point of view, but if I just give you a lattice model, I give you some symmetries, it should be very surprising to get integers.
I think I tend to agree with that. And I think the reason is just because we know in the continuum there is such a symmetry, and we just go after it on the lattice. If I didn't have this guiding principle, I could have talked about some other conserved operator which might not behave so nicely.
Okay. It could be interesting to find something.
Yeah, but maybe it will act on the local operator in an even funnier way. I don't know. Okay. Any other question? Okay. All right, so what we have just shown is that, first, it's easy to see that eta even acting on the cluster state equals to eta odd acting on the cluster state equals to cluster. And we have just reviewed why the cluster state can be viewed as a Z2 cross Z2 SPTs. But now we just find another symmetry that leaves the cluster state invariant. So in the same spirit, we should view the cluster state as a rep D8 SPT. Now, okay, so let me write it down. And here by SPT, I just mean any trivially gapped Hamiltonian whose ground state enjoy the symmetry. But the moment I say this sentence, the immediate question I always get is it a non-trivial SPT with respect to rep D8? But again, I would like to argue that the notion of trivial versus non-trivial is not always defined for SPTs. So the better question is, are there other rep D8 SPT for such that we can compare the cluster state with respect to those other SPTs? There may not be, but maybe there are.
The question about terminologies. Maybe you mentioned that cluster is a SPT. That means, well, a state is a theory. That's a bit confusing to me. A state is quantum state is the only ground state of a theory.
That's right. That's right. So, yeah. So I think T here stands for topological. So maybe I can add a num after it. I can say this is the SPT state. Right? SPT stands for symmetry protected topological state. Yeah, but I also use the word phase and state kind of interchangeably. But for this talk, I only talk about Hamiltonians, which are gap with a unique ground state. So for this class of systems, I will use the state and phase interchangeably. Okay. Okay, so the question is, are there other RAP-D8 SPTs? Sorry, let me just say that sentence. And the answer is yes. So in fact, in mathematics, it has been known for a long time that there are 3 distinct RAP-D8 SPTs.
Yeah, there you go.
Yeah, the fact that the state here has gapless edge modes, why is that not enough to claim that it's a non-trivial SPT?
Oh, wait, sorry. Sorry, I didn't understand that.
So if you put the cluster state on the interval, you have massless edge mode, like the generality there, right? Why is that not enough to claim it's a non-trivial SPT?
Yeah, so let me clarify that. So you see, I only said that the cluster is a RAP-D8 SPT. The product is not. Okay. You take that well, we can see that explicitly. Take the product Hamiltonian xj. It is not invariant under this transformation. Previously, when we talk about Z2 cross Z2, both the product and the cluster are invariant under Z2 cross Z2. That's why I put them side by side and see the edge mode. That means the product and the cluster are distinct Z2 cross Z2 SPT. Here, I have a new symmetry D. Only the cluster is invariant under D. Product is not. It doesn't even make sense to put cluster and product side by side. So that edge modes have nothing to do with the RAP-D8. That edge modes are protected by Z2 cross Z2.
If you try to put it on the open chain instead of the closed one, have the issue that D doesn't exist because there's a translation by one side.
So that's the reason why I set up the problem this way. I didn't want to talk about open chain. I want to view the open chain as a special case of this interface system between one state and the product state. And this is important because the moment you talk about a symmetry such that the product state is not invariant, the open chain is irrelevant because the open boundary condition simply breaks the symmetry. Okay. Yeah, so thanks for that question. It's actually important to clarify that. Okay, any other question before I move on? So in math, it was actually known that there are 3 RAP-D8 SPTs, and Yifan and Ryan also had a paper in the field theory context describing the 3 RAP-D8 SPTs. And in the remaining of the lectures, I will try to describe these 2 other SPTs on the lattice. And the moment we have 2 other SPTs, we can compare them. And that's the fun part. Okay, but just give me 1 second. Yes?
Last time you described the G2 or the G2 cross G2 SPTs in terms of the discrete version of H2 G2 cross G2 comma U1, but will there be similar classification for this non-invertible?
That's what I'm going to talk about now. Yeah, so yeah, I'll get to that. Yes. So for ordinary SPTs, as Max reviewed last week, you can stack them. Right? What's the idea? So if you have a G SPT, if you have a G invertible symmetry, and you have G SPT number 1, this system has a symmetry G1, which is isomorphic to G. So by G, I just mean, maybe Z2 cross Z2. The 1 here is just to say that this is the symmetry for the system for SPT number 1. I can take another SPT, SPT number 2, with G2, which is isomorphic to G. But then given these 2 SPTs, I can consider GSPT number 1 times GSPT number 2. You just you just stack them together. The tensor product theory will have G1 times G2 symmetry, where times means direct product. But in the direct product, there's a natural diagonal subgroup. Which is isomorphic to G. So by viewing this tensor product theory with respect to the diagonal subgroup, you can interpret it as another GSPT. That's why there is a stacking multiplication operation among invertible SPTs. In other words, it's an addition structure. You can add SPTs. I almost said the word that therefore they form a group, but that's not quite right because group has an identity element. This only tells you that there's a addition structure among the SPTs, but there's no canonical identity. So generally, it's a torsor over a group. And regarding to the previous question, for ordinary SPT, you should view it as a torsor over H2 of G comma U1. Yes.
There are other subgroups isomorphic to G inside G1 plus G2. Are they give rise to different?
You can take different, but that will give yeah. So you have to commit to a way to take the diagonal, and that will determine SPT for you. If you pick a different diagonal one, I think generally you get a different SPTs. Okay. However, this stacking operation or this additive structure doesn't generalize to non-invertible SPT. And that's one important distinction between the invertible SPT and the non-invertible SPT. And we can see that very easily. Let's say I have SPT number 1, which obeys D1 square equals 1 plus eta 1 even, 1 plus eta 1 odd, and similarly 2. Okay, so let's say I have two such non-invertible SPTs enjoying the RAP-D8 symmetry with this fusion algebra. And then I can consider the tensor product between the two. The tensor product theory will have D1, D2, eta 1, eta 2, so on and so on. What would be the diagonal of the two fusion categories? Well, the naive thing you would say is let's try D1 tensor product D2. But this has a problem, because as you square it, this will become 1 plus eta 1 E, 1 plus eta 1 odd, tensor product 1 plus eta 2E, 1 plus eta 2 odd. But as you do the tensor product, there will be cross terms. There will be terms that looks like eta 1 even, but identity on the right. So if you only took the diagonals, like D1 tensor D2, eta 1 even, tensor eta 2 even, eta 1 odd, tensor eta 2 odd, they are not close under multiplication. Okay. So whatever these three SPT, RAP-D8 SPTs are, there's no addition structure among them. And because of that, for ordinary SPT, it's a torsor over a group. And then you can choose an element in this torsor and say that that guy is the identity. The moment you pick someone to be an identity, it becomes a group. And that's how we usually think about invertible SPTs. But for non-invertible SPT, there's not even an addition structure there. So it's never going to form a group.
So do you get a new SPT with new symmetries, or it doesn't appear SPT?
Yeah, I guess you can say it's a new SPT with respect to the tensor product symmetry. Yeah.
Sorry, I think like the diagonal for sure doesn't work, but I think if you find a coproduct on rep D8, because the diagonal for the invertible SPTs, the diagonal subgroup is chosen with respect to the group-like coproduct on G. So if we put a coproduct on rep D8, then we would have a stacking operation.
But what would be that subcategory? Are you saying that there's a rep DA subcategory?
Well, no, I'm not saying that.
Right.
I'm saying that if you can make rep DA into like a half monoidal category, let's say, with a coproduct operation, then you'll be able to define the stacking operation.
But the point is that you want to find a rep DA subcategory in that in that delink product, so that you can view the tensor product SPT as another rep DA SPT.
Okay, yeah, that's right.
I don't think that exists.
Okay.
Okay. I have 24 minutes. All right. So now with this preparation, we can talk about. Let me first present the answer for the other rep DA SPTs, and if time permits, I will give the derivation. Maybe I want to keep that one. I want to keep this one. Okay. All right. So the way to derive this two other non-invertible SPT is to use the Kennedy-Tasaki transformation. But let me first present the answer, and then, if time permits, I'll do the derivation. For simplicity, I will assume L this time to be 0 mod 4. There's a factor 2 issue. So what are the three SPTs? We have the cluster state we already discussed. It obeys Zj minus 1 xj, Zj plus 1 equals 1 for Oj. There are two other SPTs, which I'll call an even state and the odd state. And it's important to emphasize that the product state is not a rep D8 SPT. The even states obey, it's a stabilizer state, and it obeys. It has the following eigenvalues. So still it's zxz, but x is only on the odd side, and this guy equals to minus 1 rather than plus 1. And it also obeys y2n minus 1, x2n. And the difference between even and odd, they're related by a lattice translation. Okay.
Do they have a unique ground state on the ring?
Yes.
For these two?
Yes. So let's check that. So I have a stabilizer for every side. So for the odd side, I have this. For the even side, I have this. They mutually commute. They are independent. Yeah. So I have L stabilizers on a qubit with L side. It's a quick exercise to see why I need L to be a multiple of 4. Because you can take the product of all this guy, and you want it to be plus 1.
So these three states will have some different string orders.
That's right. That's basically how we derive it. Okay, good. So this is the claim. This gives very explicit definition of the three states. Well, this tells you what the states should satisfy. But you can also write down the states very explicitly in terms of either the product state or the cluster state. Now, the first comment I would like to make first comment is that the cluster, the even, and the odd are in the same Z2 even and Z2 odd SPT. So you have a big symmetry rep D8. But if you only look at the Z2 cross Z2 invertible subgroup, then these three states are in the same class. In fact, you can even write down Z2 cross Z2 locally symmetric finite depth local unitaries relating the three of them. It's just that those circuits is not locally rep D8 invariant. Okay. And let's see that more explicitly. So as we discussed for the invertible SPTs, one way to distinguish them is to look at the edge mode. So now I'm going to put the system again on a closed periodic chain. I'm going to put the cluster Hamiltonian up here and the odd Hamiltonian down there. I didn't really write down the Hamiltonian that whose ground states give you the odd state, but it's relatively straightforward to do. Naively, you would say, let's just take those zxz and yxy terms and sum them up. However, that Hamiltonian, even though it gives the correct ground state, it doesn't preserve the non-invertible symmetry. So you have to correct it by one term. You can see that even though zxz is invariant under D, but yxy is not. So you have to add a third term. Okay. But that can be done, but let me spare you the details. At the end of the day, you can write down an interface Hamiltonian that looks like cluster on one half and looks like the odd Hamiltonian on the other half. And let's repeat the same exercise we did for the invertible SPTs and see how the symmetry operators behave this time. It's the same kind of game. You pick any ground, any states in the ground space. Any such state should obey zxz equals 1 in this region and should obey zxz equals to -1, yxy equals to +1 in the lower region. And you basically did the same kind of manipulation there and study how the symmetry operators factorize. You start with eta even, acting on any such ground state. You find that this time it doesn't factorize to anything. It just acts completely trivially. If you work out eta odd, it factorizes into eta left odd, eta right odd. Okay. So this is telling us that if you only know of the Z2 cross Z2, there's no projective algebra now, because eta even acts entirely trivially. So these two faces cannot be distinguished by just the Z2 cross Z2 symmetry. That's consistent with the comment I just made here. They are in the same Z2 cross Z2 class. To distinguish them, you really have to study how this D operator acts. There's a sign factor that's not terribly important. Okay, so we have some new features here. For invertible symmetries, it just factorizes into one term. That's a product of a local factor on the left and a local factor on the right. So this is left. This is right. But for this non-invertible operator, because of its non-invertible nature, when it acts on the ground space, it factorizes into a sum of two terms. And each term is a product of a local factor on the left and a local factor on the right. All these factors are some product of x and z, some simple Pauli operators. But let me not work out the details for you. Let me not write the details. And the moment you have this, you can check that eta left odd d left I is to minus So you find the projective algebra between the local factors of the Z2 odd symmetry and the non-invertible operator. So the system still has, the system has four ground states, this interface systems. There are two edge modes localized at the left interface, two edge modes localized on the right interface. It's very similar to the system between the cluster and the product we study over there, except that in the invertible SPT case, the edge modes are a consequence of the projective algebra between the local factors of the two Z2s. But this time, the edge modes are a consequence of the projective algebra between one of the Z2 and the non-invertible operator.
Sorry, what is the subscript for 1 and 2?
These are just two factors. There's, yeah, this, you mean the superscript or the subscript?
The superscript.
The superscript. Yeah, so the point is that the operator being non-invertible means that it cannot be just a sum, it cannot be just a single term, but it has to be a sum of two terms.
So the last line there, maybe I would have expected that D can absorb eta, but it doesn't. Is there a reason, or it's just is what it is?
It's similar to for the Z2 cross Z2 case. Naively, the global eta even and the global eta odd, they commute. They realize the Z2 cross Z2 linearly. But the local factors can be realized projectively. And one should view this as a projective version of the rep D8 algebra.
But it's not just the global phase, like the algebra.
That's right. That's right. In fact, even the word projective should be put in quotation marks.
So could we also detect this projective rotation by adding the non-invertible effect and see the response?
That's a good question. I think the answer is yes. We didn't work that out. Yeah, we really want to follow the ordinary representation of the edge mode. Okay. Any other question about?
So for 1 plus 1D group like SPT, so the boundaries, we see it has an anomaly. There's an anomaly influence, and the anomaly is a projective representation of the group.
Right.
But here, what is the corresponding boundaries?
Yeah. So again, I don't want to use the word boundary because it's really better to think about it as interface. And here, the interface is a 0 plus 1D quantum mechanics, and it just results in a projective algebra of the form AB equals minus BA.
So it's kind of some projective code representation of the categories.
Yeah, yeah.
What's D1 square, D2 square for the left, for example?
Oh, that's interesting. I don't know the, let's see, do I know the answer on top of my head? It's probably 1. I think it's just 1. I think it's just 1, yeah, because they are all product of Paulis.
It became a Z2.
Yeah. Yeah, so even, that's right. So in 1 plus 1D you have something non-invertible, but somehow when you do this quote-unquote anomaly inflow, the quantum mechanics only sees a very simple Z2 cross Z2 projective algebra. Oh, yeah. Oh, by the way, sorry, it is 1, I just checked.
It's clear that both D left 1 and D left 2 now become symmetries of the Hamiltonian?
No. So the answer is that only, I think, let me see my convention. Only this guy and this guy commutes with the entire interface Hamiltonian. And let's see, also this too, but not the other two.
So how do you think about it?
Honestly, I don't quite know, but this is the only consistent way out, right? Because you have a four-dimensional ground space, and the four-dimensional ground space, it should be a consequence of some global symmetries. Some symmetries that's AB equals a pair of AB equals minus BA. You shouldn't have more. So only these two are commute with the Hamiltonian. Yeah, that's a good question. I don't really know the conceptual reason behind. But this is the only consistent outcome that's possible. Yeah, the other two are a little bit like auxiliary for some reasons.
Can you describe how the Hamiltonians look like?
I could, yeah. It's just a little bit complicated. So deep down here is just minus ZXZ. Okay. In this region, let me first describe what's the Hamiltonian for the R state. So I have it here. So these two terms are expected because they are the stabilizers. The only issue with this Hamiltonian is that it doesn't commute with D. This term is invariant under D. This term is not. So you have to add a correction term. So it's a 5-spin interaction, ZZXZZ. And as to the interface Hamiltonian, you just put cluster in the upper half, this guy in the lower half. Okay, how much time? Well, I only have 5 minutes left. Oh, we started late. Good. Okay. So now, any other question about the claim for these SPTs? If not, I will sketch the derivation for this funny-looking Hamiltonian. It seems I literally just pulled it out of thin air. So the idea is still to follow the Kennedy-Tasaki transformation. So on the left-hand side, do I still have that? So we want to draw analogy with the third way to distinguish them over here, but generalized to RAP D8. Yeah.
In the cluster and cluster and product, you could have roughly predicted.
Sorry, cluster and what?
Cluster and product state.
Okay, and product state, yeah.
You could have roughly predicted the number of edge modes to be 4 because it was a projective representation of Z2 times Z2. Here, is it easy to see why it has to be 4?
Right, it's related to Max's question. So at the end of the day, only DR1 and DL2 are symmetries of the Hamiltonian. Okay. And DR1 and DL2 together with eta left odd and eta right are odd, they form a pair of projective algebra of the form AB equals minus BA, and that leads to the fourfold degeneracy. It's the same algebra. That's the point. It's the same algebra, it's just that it comes from different operators. Okay. So up here, on the left, we have Z2 even times Z2 odd SPTs. On the right, we have Z2 even times Z2 odd with a hat, spontaneous symmetry breaking patterns. Now on the left, we have the rep D8 SPTs. So that means we not only have eta even, eta odd, we also have this D. And we'd like to do the Kennedy-Tasaki transformation to map it to something on the right-hand side. But under this map, we will have eta hat even, which is just a product of all the x hat j on the even side, eta hat odd. But what happens to D? That's the key question. So you can show that, which I'm going to skip it, that whatever Hamiltonian you have on the left-hand side that is invariant under these three operators, after the Kennedy-Tasaki transformation will be invariant under eta hat even, eta hat odd, and a new operator V hat. Let me just write them down. This V hat, I'm really using the same notation, is the entangler we discussed earlier between the between the cluster state and the product state. But I put a hat because now we are on the right-hand side. On the left-hand side, we have a non-invertible rep D8. On the right-hand side, we have 1Z2, 2Z2, V hat, as you can easily check, is also a Z2. And they commute with each other. So on the left-hand side, we have something that's very simple. It's actually a Z2 even hat times Z2 odd hat times Z2 V hat. It's a Z2 cube invertible symmetry. It's honest to God invertible symmetry. In fact, this symmetry should look very familiar to some of you in the audience. I think the product of them is sometimes known as the CZX symmetry, for obvious reasons, CZX. It's the simplest example of an anomalous Z2 symmetry on a 1D spin chain. But here we have to discuss the separate factor between them. Okay. So the product of them, eta hat even, eta hat odd, V hat, is known as a CZX symmetry, and it has an anomaly captured by H3, Z2, U1. This is the anomaly of the Levin-Gu SPT. This is the boundary anomaly of the Levin-Gu SPT. But if you look at the individual factors, the claim is that this has an interesting anomaly in the literature known as the type 3 anomaly. The 2+1D topological action for this anomaly is A cup B cup C. Okay. So the statement is that you start with any system with a non-invertible rep D8 symmetry. You do some twisted gauging. It becomes a system with an honest-to-God invertible symmetry with a particular anomaly. And we have seen this kind of phenomena already in the first lecture, where on one side we have a Majorana chain with an honest-to-God symmetry for anomaly for an invertible symmetry. In that case, it's a translation, so it's a little bit more subtle. But on the other hand, when we do the gauging or bosonization, we find a system with a non-invertible symmetry. So this illustrates another interesting interplay between non-invertible symmetry and anomaly. Yes?
Is the role of the twisted in twisted gauging to make it into Z2 times Z2 times Z2 instead of a D8?
Yes, it's important, yeah. There's another way to get D8. There are several different ways to gauge. Here we pick a particular way to land on this. The reason we pick this particular gauging is also because it mirrors the conventional discussion of Kennedy-Tasaki transformation better. Okay, so I'm almost running out of time. Let me just say what happens to those three states. So we can start with cluster. We can start with even. We can start with odd. These are three distinct REP-D8 SPTs. After you do the TST gauging, they will become different symmetry breaking phases of this ordinary invertible symmetry. So that's the beauty of Kennedy-Tasaki, right? It transforms a subtle questions of distinguishing different SPTs into an ordinary question of distinguishing different symmetry breaking patterns. As I said earlier over there, the three non-invertible SPTs, they are in the same Z2 cross Z2 class. So if you forget about this guy, they will represent the same symmetry breaking pattern. And which one is that? It corresponds to the case when the Z2 hat even, Z2 hat odd is completely broken. So let me write it here. If you start with cluster, you go here, that corresponds to the case when only Z2 V is unbroken. Okay? Z2 even, Z2 odd is completely broken.
That's give a 4 degenerate ground state.
That's right. That's right. In fact, it's literally the same Hamiltonian here. If you have a Z2 cross Z2 cross Z2, and you know these two are completely broken, this is not the only option. You can also have this being the unbroken subgroup. So the important thing is that if you have a big group and part of it is broken, part of it is unbroken, the unbroken part is a subgroup. The broken part is a quotient. Here we only know the quotient part. So to determine which, determine the symmetry breaking pattern, I have to specify the unbroken subgroup. For the cluster case, it's Z2V. For this even guy, it's some diagonal subgroup of Z2 odd with this new player in the game. Similarly, for Z2 odd, this is the diagonal of Z2 even and Z2 V. Okay? So the name of the game is that using the Kennedy-Tasaki transformation, we transform the problem into finding Hamiltonians for conventional symmetry breaking. So it's easy to deal with the problem on this side. You can just try to come up with some simple Hamiltonians in the hatted frame that represents this particular symmetry breaking patterns. And then you can undo the Kennedy-Tasaki transformation and therefore derive the SPT Hamiltonian. Now, for those of you who are still awake, there's an obvious puzzle here, which is that I can take Z2V to be unbroken. I can take the diagonal between odd and V to be unbroken. I can take the diagonal of even and V to be unbroken. But there's one more option. What about the diagonal of Z2 even, Z2 odd, and Z2V unbroken? That's right. So naively, there is this fourth option, which would lead to a contradiction, because mathematically there are only 3 such SPTs. But this option is impossible. The reason it's impossible is because the generator of this guy is precisely the famous CZX symmetry, which famously has a Levin-Gu anomaly. If you have a anomalous global symmetry, you cannot find a phase where the anomalous symmetry is unbroken. A gap phase where the anomalous symmetry is unbroken. So this possibility cannot be there. And that's consistent with the fact that we only have 3 SPTs. Okay, so with that, I think I'll just conclude here. Thank you.
Is there a possible way to detect the distinct 3 SPT in not consider the interface, but only consider the both?
Ah, you mean by inserting some defects?
Yes.
Possibly. Yeah, we just didn't work that out. Yeah, very likely. Yeah.
So in principle, you can still do stacking in a sense. You just say the D1, D2 as a symmetry, then any local operator commute with that will be allowed.
It's just
the complaint is that after stacking, since the real symmetry of stacking the model is changed.
That's right. That's right. You can definitely stack the physical system. It's just that the new system is.
You find a new symmetry of a stack.
That's right. That's right.
But symmetry is not the same.
That's right. Yeah. Exactly. All right. Okay. Then I guess it's time for lunch.